Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss acoustical and optical phonons. Let's begin. In the previous video lecture, we have already derived the dispersion relation of linear diatomic lattice vibration. That is the expression for the dispersion relation for linear diatomic lattice vibrations, and it has two values. One value is positive, another one is negative, as there will be plus and minus. Dispersion relation is the relation in between omega and k. So, if we plot a graph between omega and k, that graph gives us two branches of dispersion relation curve. Two branches of dispersion relation curve, one branch for omega plus, another branch for omega minus. So, one curve corresponding to omega minus is called acoustical branch, and another corresponding to omega plus is called optical branch. So, if we plot a graph in between omega and k, omega along y axis and k along x axis, it has two branches, lower and upper. That lower branch represents for acoustical branch, omega minus, upper one for optical branch, omega plus. From the region minus pi by 2a to plus pi by 2a, that one is the first Brillouin zone. That region is the forbidden region, forbidden frequency band. Now, we have to understand in detail about acoustical branch and optical branch. Now, what are the frequency ranges of these two kind of branches? First one, for optical branch, that is case for omega plus. Omega plus is represented by optical branch. In that of graph, the figure is looking like this. Now, we mathematically show what will be the frequency region. The upper branch of that of dispersion curve is called the optical curve, as we shown in that of figure. For that of optical curve, k tends to 0, therefore sin k, sin 0 as 0, that is its value is negligible. Hence, if we put sin Ka is equal to 0 in the dispersion curve relation, we have for omega plus, if we put sin Ka is equal to 0, so that entire term vanishes, under root of that 1 by m1 plus 1 by m2 whole square, its under root just 1 by m1 plus 1 by m2, alpha 1 by m1 plus 1 by m2 plus alpha equal into 1 by m1 plus 1 by m2, that is 2 times of alpha 1 by m1 plus 1 by m2. If we just calculate only omega plus, then it will be under root of 2 alpha 1 by m1 plus 1 by m2. So that value omega plus is equal to 2 alpha 1 by m1 plus 1 by m2 under root. Then what be the maximum value of that omega plus? For achieving that one, we have to take k tends to plus minus pi by 2a. Therefore, sin Ka tends to 1, and we have putting these values in that of expression for omega plus. You have omega plus square is equal to alpha whole into 1 by m1 plus 1 by m2 plus alpha whole into under root of 1 by m1 plus 1 by m2 whole square minus 4 divided by m1 m2. Here a plus b whole square, a square plus b square plus 2ab, in 2ab, that is 2 divided by m1 into m2, 2 divided by m1 into m2 minus 4 divided by m1 in m2. Finally, we achieve minus 2 divided by m1 into m2. Therefore, the entire term will be 1 by m1 minus 1 by m2 whole square. Therefore, we have alpha 1 by m1 plus 1 by m2 plus alpha 1 by m1 minus 1 by m2 whole square, its under root. So, 1 by m1 minus 1 by m2. Again expanding this bracket, so the minus term and plus term cancel out, alpha divided by m2 minus alpha divided by m2 cancel out. We have 2 times of alpha divided by m1. Therefore, omega plus square is equal to 2 alpha divided by m1 under root. That is omega plus 2 alpha divided by m1 under root. Here omega plus value is 2 alpha 1 by m1 plus 1 by m2 under root. Therefore, omega plus values varies from this region, omega plus values as this to that. So, in that of curve we show it that curve for optical branch. For optical branch, that point the frequency is 2 alpha 1 by m1 plus 1 by m2 under root, and at that end the frequency 2 alpha by m1 under root 2 alpha by m1 under root. That is for optical branch. Optical branch, that with the frequency as we show in mathematically. So we write it. Hence, the optical branch starts with frequency 2 alpha 1 by m1 plus 1 by m2 under root at k is equal to 0 and decreases slowly with increase in the value of k and ends with frequency 2 alpha by m1 under root at k is equal to plus minus pi by 2a that also is shown in that of figure for optical branch, that frequency varies from these two. That important point for that of optical branch. Another point for that of optical branch, what should be the amplitudes? To show that, we have to idealize for optical branch as k tends to 0, so cos of k tends to 1. So the equations we have discussed in linear diatomic vibrations. So see these equations, two varieties of equations we achieve. As we say, cos k is equal to 1. So instead of that value as 2 cos k, so in that place we use cos k is equal to 1. So we achieve two kind of equations. So the equations as minus omega square m1a is equal to 2 alpha b minus 2 alpha a, one kind of equation. From that equation we can find minus omega square m1a is equal to 2 alpha as common b minus a, or negative is multiplied here. So we have omega square m1a is equal to 2 alpha a minus b, or minus omega square divided by 2 alpha is equal to a minus b divided by m1a. And another pair of equation, another one of that pair, as minus omega square m to b is equal to 2 alpha a minus 2 alpha b. In that particular situation we use cos k is equal to 1, or minus omega square m to b, 2 alpha is common, a minus b, or omega square divided by 2 alpha. In that of side we have minus a minus b divided by m to b. Look at these two equations. Let equation number I and equation number double I. From 1 and 2, from equation I and double I, we get here the LHS and RHS are similar. For omega square 2 alpha, here omega square 2 alpha is equal minus of that much. So minus of a minus b divided by m1a is equal to minus of a minus b divided by m2b, or we have a by b is equal to minus m2 by m1. A by b is equal to minus m2 by m1. This indicates that the two atoms in diatomic case, one having mass m1, another having mass m2, whereas the mass of m2 is greater than mass of m1. So the two atoms move in opposite direction and their amplitudes are inversely proportional to their masses, as is shown in that of equation. So that we can say the center of mass of unit cell, remain unchanged, if m1 is equal to m2, two masses are same. At that of condition, a by b is equal to minus 1. That indicates even if their masses are equal, the atoms always move, sign is negative, always move in opposite directions. Graphically we show in optical branches, or when the frequency of any kind of wave having that allowed frequency, the particles are vibrating in the tap the M2, and that scenario M1 is vibrated, just its opposite. Heavier masses, these are the lighter masses. This is for optical phonons. From that expression we say two masses move in opposite direction and their amplitudes are inversely proportional to their masses, and at that of case also their masses are equal, the atoms always move in opposite directions. These 2 points for optical branches. Optical branches, if we apply the frequency like that of light, then inside that of crystal the lattice are vibrated like that of optical branches. Next, acoustical branch. Acoustical branch, case of omega minus, the lower branch of dispersion curve is known as acoustical branch. See that of figure, that lower branch that represents for omega minus is known as acoustical branch. Then we mathematically show what be the frequency range of that acoustical branch. Example of acoustical branch applying the wave as sound wave. If sound wave is implemented to that of crystal, then the vibration of that lattice points like that of acoustical branch. In acoustical branch, for k is equal to 0, sin k 0, sin 0 0, hence omega minus is equal to omega minus sin 0 0, that term cancelled out, it is root over 1 by m1 plus 1 by m2, here is the minus, so omega minus is equal to 0, omega minus is equal to 0. One frequency range we achieve. Next, for taking Ka is very less than equal to 1, at that of case sin Ka is equal to Ka sin theta is same as theta. Now omega minus square is equal to alpha 1 by m1 plus 1 by m2 minus alpha 1 by m1 plus 1 by m2 whole square minus 4 k square a square divided by m1 m2. Here in place of sin Ka we replace Ka, it is under root, is equal to, from that root over term we take common as 1 by m1 plus 1 by m2 whole square. throughout that of these two terms entirely we take in common as alpha 1 by m1 plus 1 by m2 common in these two terms. So here we have 1 minus, then inside that of root over term we have 1 minus, so that term 4 k square a square m1 m2 divided by m1 plus m2 whole square. Now alpha we can write that term as m1 plus m2 divided by m1 into m2, taking its LCM and adding these two. When we evaluate binomially of that under root term, so that evaluation takes place 1 plus next terms, so 1 minus 1, so 1 cancelled out, next another terms are exist, so the higher terms we neglect. Here we write using binomial expansion and ignoring higher power. Just we have 2 k square a square m1 m2 divided by m1 plus m2 whole square, just 1. Here binomial expansion there will be a term 1, so 1 minus 1 cancel out, another term starts with this, then the higher terms are neglected, so that term only exists, next terms we have neglecting as it taken the higher powers. It will be 2 alpha k square a square divided by m1 plus m2, here m1 m2 cancelled out, m1 plus m2 1 m1 plus m2 cancelled out, therefore omega minus is equal to Ka 2 alpha divided by m1 plus m2 under root. That frequency varies from 0 to this. Now in graph we show that frequency range as 0 to that of frequency range. Okay, looking at that situation, when sin square Ka is equal to 1, therefore Ka is equal to plus minus pi by 2, sin pi by 2 is equal to 1, that is for maximum situation, that is the maximum value. So m1 replaced by m2 in the previous expression, and its solution is written as omega minus is equal to that previous expression, here 2 alpha by m1 under root, but at that of situation k is equal to 1 and in place of m1 we just replace as m2. So, omega minus as 2 alpha by m2 under root, that for omega minus maximum. So, in that of frequency range, that is 0 to 2 alpha by m2 under root. Okay. Next, what be the amplitudes? For amplitudes, we show for acoustical branch as k tends to 0, therefore cos k tends to 1 minus k square a square divided by 2. Then the pair of equations, in place of this substitution we just use that value. So, the pair of equations are as previously we found omega square m1 a is equal to 2 alpha b 1 minus k square a square divided by 2 minus 2 alpha a, one pair, and another one is minus omega square m2 b is equal to 2 alpha a 1 minus k square a square divided by 2 minus 2 alpha b. Now adding 1 and 2, adding 1 and 2 we get minus omega square as common m1a plus m2b is equal to minus k square a square alpha a plus b. The terms are cancelled out, only the terms exist. Again we put the value of omega here, value of omega as k square a square two alpha divided by m1 plus m2. Value of omega, we chosen the value of omega from this. So, m1a plus m2b is equal to minus k square a square alpha a plus b. On both sides the terms are cancelled out, k square a square minus alpha, and we have that m1 plus m2 is multiplied here. So, we have m1a plus m2b is equal to m1 plus m2 whole into a plus b. So, it is written as m1a plus m1b plus m2a plus m2b. So, m1a m1a cancel out, m2b cancel out, so only we have m1b plus m2a is equal to 0. Here m1a m2b m1 m2 m1a m1a m2b just have m1b minus m2a. Okay, there will be term 2 is exist. Oh, I'm extremely sorry. One term 2 is exist. So one term already have existing there. Okay. So one term is exist m1a plus m2b, another as m1b plus m2a. Therefore we choosing it as m1a minus m2a, here m1b minus m2b, or m1 minus m2, a has common, here m1 minus m2 b has common, these two are cancelled out, therefore a by b is equal to 1. That is positive. That positive indicates, this means the two atoms with different masses move in the same direction, and the ratio of their amplitudes is positive. Same direction with same amplitude, and there is a movement of their center of masses, as well. In graphically we can show it as, we show it the acoustical branch, the moment is one big another small, 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 one big. The movement of particle, that of acoustical branch, each has same amplitude and movement along same direction. Different masses move with same direction with same amplitude. These are for small masses. that for acoustical branch. So here with the help of this video lecture we understand the concept of acoustical and optical phonons. This is the graph of acoustical and optical phonons, and mathematically we show for optical branch that for omega plus, that is the frequency range, and from that of particular expression we show what be the amplitudes and their propagation of atoms. Next for acoustical branch, that with the frequency range 0 to 2 alpha by m2, and again a by b is equal to positive, that indicates what be the amplitudes and the direction of propagation of atoms in that of acoustical branch. So with this useful and informative notes, let me wind up this session. Thank you.